On Christmas Day 2021, the largest space telescope ever built was launched into space. This was the James Webb Space Telescope. It does amazing things. It looks at the formation of galaxies. It looks at some of the earliest stars and also the planets going round those stars. But most crucially, it's probably our best tool for finding alien planets and possibly the aliens themselves. So we're going to continue our journey from the solar system, through our galaxy, and out to the known universe as we continue asking the question, are we alone?
Leaving Earth orbit.
Houston, we've had a problem.
Take third exit to Mars. Mars rover collected. Warning. James Webb Telescope. Acquired. Navigate off-road. Voyager probe acquired. Approaching light speed.
Welcome to the 200th anniversary of the Christmas lectures from right here in the Royal Institution, supported by CGI. Now, my name is Dame Dr. Maggie Aderin-Pocock, and I'm a space scientist and a science communicator. Now, I built instrumentation that help us to better understand the universe. Now, going back to that Christmas day in 2021, my daughter, who was then 11, was opening her presents. I was distracted. All I wanted from Santa was the safe launch of the Webb telescope into space, a huge global project in which I played a small part. Now, the main feature of any telescope is, of course, its mirror. And of course, the bigger the mirror, the more light it can gather. Now, this is the size of the Hubble Space Telescope. It is 2.4 meters in diameter. You can see it's a lot taller than me. Now, Hubble sits in low Earth orbit, about 500 kilometers above sea level. And from there, it's taken some fantastic images of the universe and transformed our knowledge. But this is the Webb telescope. And this is actual size, 18 segments, all put together to make this fantastic mirror. Now, James Webb is detecting infrared light, and infrared radiation has a much bigger wavelength. But the challenge is this: how do you get something this size, along with a heat shield, into space? Well, to explain that, we used origami and inspiration from nature. So this is the James Webb Space Telescope. And as you can see, it's unfurling here. So there's the mirror. This is the giant heat shield protecting it from radiation from the sun and Earth. And what it's doing is deploying all these mechanisms so that it can be ready to detect infrared light out there. And the final bit's the mirror coming into place, just as we've done here. Thanks, guys. Now, unlike Hubble, Webb sits 1.5 million kilometers away from Earth. But why go to the trouble of sending a telescope out into space so far away? Well, Webb's location is needed partly because it needs to be up above the atmosphere. The atmosphere absorbs infrared light, so we need to get it up above the atmosphere so Webb can do its work, detecting that light. But my favourite thing about James Webb is the wonderful pictures it takes. And here are my top 3 pictures. Coming in at number 3, this is the first image, and it's actually of the planet Neptune. But one of the things we can see is one of the rings around Neptune. Now, many people don't realise, but all the outer planets from Jupiter onwards, they all have rings. We know about Saturn's rings, but we don't often see the rings of the other planet. But using this infrared light, we suddenly see a familiar planet, but in a detail that we're not used to. OK, coming in at number 2, it's this image. Now, this image is looking back through time. So this is showing us sort of ancient galaxies. So many of these galaxies no longer exist. But what we're seeing here is a number of different stars, and this is some of the earliest galaxies that ever formed. But my favourite picture is called the Pillars of Creation. Now, this was first photographed back in the 1920s by a scientist called John C. Duncan. And he used a black and white photographic plate Now, the image we have here is actually taken by the Hubble Space Telescope. But now, this is the Hubble image, so we're looking at invisible light. But let's fade that into the James Webb Space Telescope image. And suddenly we're seeing a lot more stars. So see, these stars are giving out lots of infrared energy. Also, I'm going to come around this side because these are the pillars of creation. And up here and here, we've got these red areas, and these are known as stellar nurseries. These are where new stars are being born. So that's the joy of it. With the James Webb Space Telescope, we're looking at our universe, but in a slightly different way. So these images are absolutely glorious. But what if you could transcend our atmosphere and experience firsthand that view from space, just as Hubble and Webb do? Now, to hear from someone who's actually made that journey, I would like to invite to the theatre the astronaut, Tim Peake.
Hello, Maggie. Hello, Maggie.
Hello, Tim. Now, what we've got going on behind us, because it's nearly 10 years to the day since you launched into the space.
Yes.
And last time you did a Christmas lecture, because you've done one before, but last time you did a Christmas lecture, you actually did it from the International Space Station.
That's right.
Is it good to be in here in the theatre now?
Oh, it's fantastic to actually be back down on Earth. But I have to say, I did enjoy my time up in space, and that was so exciting to be able to come down in 2015 and join you from the International Space Station.
Now, one of the things that I've heard when I speak to astronauts is that when you're living on the International Space Station, one of the places that people love to go is something called the cupola.
That's right.
Yeah. Now, can you explain what that is?
Absolutely. So this is the International Space Station, and this is the front of it. So imagine that the space station is flying towards us out the screen. But if we rotate this 90 degrees, we'll look down the length of the space station. And actually, this thing's about the size of a football pitch, so it's quite big. But whenever you get any free time at all the astronauts, we like to grab a camera and go to this cupola window here.
OK, so that's that nodule there.
That's right. If we turn it a bit more, we'll see it a bit more clearly. And the reason being is as the space station orbits the Earth, we constantly pitch down like that. So this cupola window is always facing planet Earth. Ooh. And so when we go there, you can fit your entire body into that window, actually, and just look down and see the stunning view beneath you. It's constantly changing by day, by night. We never get bored. And by the daytime, you just see all of Earth's geology, the desert, the mountains, the cloud formations, the stunning colours of planet Earth. And then by night time, it's so easy to see that we live on a planet of inhabited, people who've discovered electricity, because we see the cities, the motorways, the lights and everything. And also we see thunderstorms, we see the aurora, the northern lights, the southern lights, and it's utterly magnificent.
Oh, yes. See, all my life I've wanted to get out into space, so just that description, just sort of, whoa. Do you think it changes your perspective to see the universe spread out in front of you like that?
Oh, it completely changes your perspective of our planet, because you see it against the vast black backdrop of space. But also it changes your perspective of is there life out there? When you see that abundance of stars in our galaxy, it does make you think, there has to be life out there somewhere.
So you're a believer? You do believe there's life out there?
I am a believer, yes.
I love it. Optimism, that's what we need. So thank you so much, Tim, and I think you'll be joining us again later.
Excellent. Thank you very much, Maggie. See you in a bit. Bye-bye.
Thank you. So Tim went to the International Space Station, which sits about 500 kilometres above sea level. But on our hunt for alien life, we're going to need to go much, much, much further. And so our new playground is our home galaxy, the Milky Way. So bring on the galaxy! And here it is, our home galaxy, the Milky Way. Now, we call it the Milky Way, but if we look back at other cultures and back through time, other people have called it other names. In the Kalahari Desert in Africa, it was known as the backbone of the night. Now, the name Milky Way actually stems from a Greek legend, which was about Hera, a goddess who was breastfeeding the infant Hercules. And what happened is Hercules came away from her breast and the breast milk spilt across the sky, and they say that's what formed the Milky Way galaxy. But it is actually gorgeous, and it is a collection of many, many, many stars. One of the questions is, where are we in this Milky Way galaxy? And I think I've got, thank you very much. And I think I've got, a little you are here sign. And that sits about here. So we sit in one of the spiral arms of this amazing galaxy. Now, how do we know that? And one of the things is, we believe that the galaxy looks like this, but we've never actually taken an image of our whole galaxy. That's because the galaxy is so huge. We can't travel far enough away from it to take the whole picture. But what we can do is we look out in space and see other spiral galaxies, and we're pretty convinced that this is the view. We are in one of the spiral arms of our galaxy. Now, humans have mapped the stars for thousands of years, from the ancient Babylonians who draw pictures to the last century where we were using photographic plates. But now we know more about the galaxy than ever before, thanks to a spacecraft called Gaia. So Gaia has been out there in space for 12 years now, and it's creating the most detailed 3D map of the Milky Way that we've ever made before. Now, to find out more about this and discover what Gaia has found out so far, I'm thrilled to invite to the stage my Sky at Night co-presenter and galactic scientist, Professor Chris Lintott. Good crowd, good crowd.
Nice spaceship.
Hey, walk right.
Careful.
Yeah.
This is great. You should stay here all the time.
Actually, I mean, this is my home away from home now.
Okay,
Yes.
good.
You can come on board whenever you like.
Thanks, Maggie.
So tell us a bit more about Gaia. First of all, how does it work? And actually, sorry, just to start with, this is the Gaia spacecraft sitting out there in space.
Yeah, so the magic thing about Gaia is it's only a small telescope, but it does a really clever thing. It measures the distance to stars, and I can show you how it does that with nothing more complicated than your finger.
Okay.
So if everyone in the audience and everyone at home gets a finger, and I want you to line it up with something in the background, and then I want you to shut one eye, and then switch to the other eye, and you can go back and forth, and what you see is the finger jumps from one side to the other.
Yeah, so the background seems to change
That's
quite
right,
radically.
exactly. And then if you move the finger further away, so at arm's length, and you do the same thing, so one eye, then the other eye, and then back, what you see is that the finger still moves, but a bit less.
Okay, lovely. Okay, and so let's go to the ultimate distance. I'm standing here on the stage, and if you look at me and then shut one eye and then the other eye, you can see that the distance is now quite small. The background hardly seems to move behind me.
So that means by measuring that shift, if you observe something from two different positions, you can get a distance. And that's what Gaia does. Now, the trouble is the stars are a long way away, so the shift is really small. And so it uses not two eyes, but two sides of the Earth's orbit. So it observes the same stars 6 months apart, and then we get the distance. So we get a three-dimensional map of the galaxy, but we can also measure how the stars are moving.
Okay.
So we can see the velocity of things as well.
Lovely. So that's it. So Gaia's been out there for 12 years. So what's it been telling us?
Well, my favourite thing is that we can predict the future. So this is a map of the million nearest stars in the Milky Way, and we can show you the next 1.6 million years.
Okay,
So
that's
this
it.
is the future of the night sky, because the galaxy is changing.
Oh,
It's
so we
evolving.
think of the stars of the night sky as static, but this is sort of projecting into the future.
That's right.
And
My
it does-
favourite thing is you see these fast ones that zip
Yes,
round.
zip round.
They're popping in and out of the pancake of the Milky Way, so they're rather special stars. So because we can do this forwards,
Yes.
we can also go backwards.
Okay.
And so we can plot the past of all the stars in the Milky Way, and that's told us that our galaxy is assembled violently. It eats other galaxies.
What?
And we see these streams of stars which are like the leftover dessert. So they're remnants of galaxies that our galaxy has consumed, and they've got brilliant names, these old galaxies that we've eaten. There's one called the Kraken, which is a sea monster. My favourite's one called the Gaia Enceladus sausage, which is just lovely. But there's something special that happened 5 billion years ago.
Okay.
So this is the Sagittarius dwarf galaxy.
Okay,
This is a simulation.
So this is
yeah.
a cluster of stars.
Yeah, and 5 billion years ago, or 6 billion years ago, it came close to the Milky Way. The Milky Way sparkles, and this thing gets flung out. It stretches out into this beautiful stream, and then 2 billion years ago, it comes close again. And today we see it in the Gaia data as these long streams of stars. Yes. But what's special is that I said 5 or 6 billion years ago.
Yes.
Now that's the time that the sun was forming. And this encounter with this tiny galaxy may have kick-started a lot of star formation in the galaxy, and it may be the reason that we're here. Our sun might have formed in a burst of star formation that was formed by this Sagittarius dwarf.
Yeah, so that's the sparkle we saw earlier. So what I want to ask you is, in the current time, how many stars do we think are in our galaxy?
Gaia's looked at 2 billion stars.
Oh, right, yes.
And that's a fraction of the whole. So we think our galaxy's got between about 100 billion
Okay.
and 400 billion. We're very bad at counting the small ones, but let's say at least 100 billion stars, and you won't go wrong with that.
Lovely. So we're going to take as our baseline 100 billion stars, and that's in our galaxy. And so that is a heck of a lot of stars.
It is.
Thank you, Chris. You're going to join us later, but
will.
thank you so much for joining me now.
See you soon.
Thank you. So we settled on the number of around, give or take 100 billion. And so that is quite a mind-boggling number. But now what we're trying to do is detect exoplanets, planets going around the distant stars we see in the night sky. And of course, if they are reflecting the light from their local star, we can barely make out the star. How are we going to see that reflected light? So we need another way of detecting exoplanets, and we need to get clever. So first of all, I'd like to introduce another method, and we call it the wobble method, and I think you'll see why. And so for this, I need to call down a volunteer. OK, perfect. I think, yes, would you like to come up? Yes, please. I just love your hat, so... So first of all, yes. So first of all, what's your name?
Liam.
Liam. Thank you very much, Liam. Now, what we're going to do is we're going to try and detect exoplanets. But first of all, if you'd like to stand in front of this star. So what we have here is a star. And it's a star, a distant star, sort of trillions of kilometres away from us. And what thing is, so we can't see the exoplanets going around the stars, but we can see the stars themselves. Now, first of all, we've got this star, and it hasn't got an exoplanet around it. Now, I don't know if you can see how it's hooked there. What I'm going to do is we're going to give you a countdown, and then sort of after 3, 2, 1, I want you to unhook it, and we're going to see what happens to this star. OK, so are we ready? 3, 2, 1. Ah, yes. You have to hook it. Yes. OK, so just like our star, this star is spinning on its axis. But as you can see that it's sort of not much movement there. It seems to be spinning on its axis, and we're not getting much wobble. So that is a standard star without an exoplanet going round it. But of course, we have Exhibit 2. Now, this is a star, but now we have an exoplanet in orbit around this star. And what we want to do is compare the movement of this star with the movement of that star. So are we ready? OK, so 3, 2, 1. It's fiddly, but here it goes. And so now, do you see what's happening? The star is wobbling and gyrating because of the presence of the exoplanet. It makes it unstable, and so it sort of moves around in this way. And now, we can't see the exoplanet from space, but we can see the star wobbling because we do see the stars. And so this is what we're looking for, the wobbling of stars, and that indicates that there might be an exoplanet in orbit about it. So thank you. A round of applause for our volunteer. Thank you very much. So this seems like a great way of detecting exoplanets. But the problem is we can only detect the larger exoplanets. And so we're talking about sort of Jupiter mass exoplanets and in tight orbits around their star. But that's not really what we're looking for. We're looking for Earth-like planets with a sort of a broader orbit because they will sit in the habitable zone. And so we have another method, and that's called the transit method. And funnily enough, we have a demonstration for that too. So now, once again, we have our star in the middle, and now I think back here you might be able to see we have an exoplanet in orbit. And what I'm going to do is I've pressed the right button. OK, our exoplanet is orbiting around the star. Now, imagine that we are back here on planet Earth, and we're looking up at this exoplanet in space. The star itself is giving out a lot of light. But what we have here is a meter sitting on planet Earth. OK, yeah, so we're just going to dim all the lights. And this is actually reading out what this light meter is detecting. So at the moment, it's about sort of 37, 38. But when an exoplanet goes between the star and us, we should hopefully see the light signal dip down. So there we go. Did you see it? It went down to 15, and then it came back up again. And so we can detect exoplanets this way, using this transit method, as the exoplanet goes in front of the star. And this is actually closer to the data we really get. We actually have what we call a light curve, and it shows how the light changes as the exoplanet goes in front. So here it is. So that's without the exoplanet. That's the exoplanet going in front of the star, and then the light level goes back up as it comes out the other end. And so that is the transit method. But using the transit method, we can tell a lot about what we're observing. And so as the exoplanet goes in front of the star, depending on how much starlight is blocked out, we can actually get an indication of how big that exoplanet is, of how big its orbit is around the star. We can tell a lot of things about it just by looking at this light curve. And using this technique, we have found many thousands of exoplanets. So to date, we've got about sort of 6,000 in the bag. OK, so using the transit method, one of the questions we're trying to ask is, are they habitable? And so how do we find that out? Well, it turns out that the transit method can help us with that too. And for this, we've got another demonstration to show you. It's all based on something called spectroscopy. Because what we can do is actually, as the starlight passes through the atmosphere of an exoplanet, it's a tiny, tiny fraction of starlight, but we can actually look at that starlight and analyse what elements are in the atmosphere of an exoplanet trillions of kilometres away. So what we're doing here is mimicking that transit method that we discussed earlier. So what we have here is a bright source, and that is representing the local star that the exoplanet is going round. Then here we have the atmosphere of the exoplanet. Okay, then over here, what we're doing is we're taking the light from the star that's passing through the exoplanet's atmosphere, and we're analysing it. We're using this technique called spectroscopy. So let's dim the lights. Let's set that atmosphere alight. Okay. So now, here we have our spectrum of colours. So as it passes through this piece of equipment called a grating, it is stretching the light out into its component colours. And we can see that on the board here. Now, Fergal, what you're going to do is you're going to add a compound to that atmosphere, aren't you? And it's going to burn. So what compound are you adding?
So this is sodium bicarbonate. So
Sodium bicarbonate.
The same stuff you would put in cakes.
Now, what happens is, as we add that to the atmosphere, some of the starlight will pass through the atmosphere, but with the sodium bicarbonate, because it's a sodium-based compound, we will actually get absorption. And so as Fergal adds the sodium bicarbonate, we get a dark band. Now, that is known as an absorption band. OK, yeah, I don't know if you can see it just there. And so, as you can see, the flame is burning very yellow. Sodium compounds sort of absorb that yellow light. And that's what we're seeing here, the absorption of that sodium band. So thank you very much, Fergal. So that's what's happening in the atmosphere. We have in the starlight of the distant star, it passes through the atmosphere of the exoplanet, and depending on what compounds are in that atmosphere, some of the light will be absorbed. And we can actually see that here. And this is what we were seeing. So I don't know if you noticed, the band was sort of in the yellow. And so that's probably the yellow sodium doublet there. But other compounds sort of also produce these absorption bands. And so we've got sodium there, we've got nitrogen, here's hydrogen, and these are where the absorption bands occur. So when we look at an atmosphere, we get a distinct fingerprint of these absorption bands, and that tells us the chemical composition that that atmosphere has. Now remember, these are exoplanets, trillions of kilometres away from us, and yet we can actually do some remote control chemistry and work out what the composition is. Thank you so much, guys. Now, analysing the atmosphere of exoplanets can tell us whether they might be habitable, but can it actually detect life itself? Well, not exactly, but it can give us an indicator. There are certain molecules that occur on exoplanets and right here on planet Earth that are what we call biosignatures. Also, they're quite unstable, so they break down quite quickly. So when we see one of these molecules in an exoplanet far, far away, the question is, have they been generated by life? To find out more, I'd like to introduce, from the University of Cambridge, Professor Niku Madhusudan. Now, Madhu, if I may, thank you. Now, tell me about, because you made the headlines earlier this year. You made the headlines because of a planet called K2-18b. Now, this is an exoplanet. And what you detected was, I guess, a biomarker. So can you tell me about this?
So this planet, K2-18b, is about 9 Earth masses in mass. And
It's quite big.
It is quite a big planet, and 2.5 Earth times the size of the Earth. So 2 years ago, we had already made the first detections of carbon-bearing molecules in this planet, methane and carbon dioxide. So we think this is what is known as a Haitian world. It is the possibility is that it's an ocean-covered surface with a hydrogen-rich atmosphere, and that it could be habitable. Okay. In other words, the conditions in the oceans could be conducive for life. So already 2 years ago, we saw a tentative hint of this molecule called dimethyl sulfide in the atmosphere of this planet. We weren't sure at the time. But this year, what we published was a second observation with a different instrument where we continue to see tentative hints of this molecule. Okay. Now, DMS is interesting because it's a molecule produced primarily by life
Now, on Earth, this is, I guess, plankton.
Right.
Okay, so these are sort of microscopic sort of organisms that live in the ocean, and they produce the molecule DMS.
That's right.
And the fact that we found this compound on another planet, it does seem incredibly exciting. One of the questions we have asked throughout time, are we alone? And this is getting closer to answering that.
That's right. The excitement here is that even though we are at a very early stage and it's too early to claim that we have detected life, the fact that we are seeing molecules like this means we have the technology to be able to detect biomarkers in exoplanets. This particular planet is hundreds of trillions of miles away. So the fact that we're able to detect even a tentative hint of such a planet from such a distance is immense, and that leaves the door open to what else we can discover on such planets.
Yes, and the fact that these observations are coming through the James Webb Space Telescope, this is the best piece of equipment we have out there. But of course, we have other things in the planning, and so maybe these sort of detections might be easier in the future.
Yeah, the search for life is such a fundamental quest that no amount of observation time is going to satisfy our curiosity to look for what else is out there.
So thank you very much, Nadu. But don't go yet. If you'd like to step this way,
yes.
We have a little bit of fun for you in the audience. Because we've talked about sort of, the possibility that, sort of life is out there. But what would creatures like that look like? Would we just find sort of, biological organisms or something very simple? Or what would alien life actually look like out there? And so what I want you to do is join me in a game show, and the game show is called Draw That Alien. Okay. Thank you very much. Thank you. This is me getting into game show host mode. Now, first of all, I'd like to invite Tim Peake back to the stage. Come on down, Tim.
All right, thank you very much.
Thank you. So, Nadu, please, you're going to be part of the host for Draw That Alien. OK, so first of all, we are going to break up this lecture theatre into 3 parts. You middle section, you are my section. Tim, this is your section. And Nadu, this is your section. Now, what I'm going to do for each section, I'm going to give you a real exoplanet. And I'm going to tell you the tentative information that we have about each of that exoplanets. And so what I want you to do is, when I describe this planet, I want you to draw that alien. OK, now let's start with my section. Our planet is K2-18b. Now, it's a water world. So start drawing the alien. What sort of alien do you think might be on a water world? Now, what do we know about this planet? Well, the information is a little tenuous, but we think its size is somewhere between Earth and Neptune. So it's sort of like a super-Earth or sort of a Haitian planet, as we mentioned. It has an atmosphere, probably, which is thick in hydrogen, and it's mostly completely covered in water, and the average temperature is probably about 0 degrees. Tim, we're coming over to your section. Perfect. Now, you have TRAPPIST-1e, one of the planets of the TRAPPIST system. Yeah. OK, now TRAPPIST-1 is a rocky planet. And now let me give you a bit more information about this. Now, size is quite similar to Earth, so this is looking quite promising. It sits in the habitable zone of its star. So,
excellent. But,
unfortunately, it has a violent star. This means extreme radiation. OK, Nadu, over to your section. Now, your planet is LHS1140b. Now, this is an ice planet. Now, this is called a super-Earth because its diameter is about 2 times the size of Earth. We think it's got an icy surface, but it is very, very windy. But it has a light, puffy atmosphere, mainly made out of hydrogen and helium. Now, in the meantime, I'm going to come and see my section. So I'm coming up here. So how are your pictures coming along? What have we got? OK, lovely. I can see, oh, gosh. I can see a lot of artistic interpretation here. Now, what I need to do is select it. So can you hold them up so I can see them? Fantastic. Ooh, OK. Oh, my goodness. I've got to choose one as an example to bring down. Actually, I quite like that one. Sorry, yes, with the 2 googly eyes. Thank you. Can you pass that up? Thank you very much. Very artistic. Fantastic, thank you. So in a minute, I'm going to cause a halt, but I'm going to take this one down. Tim, how are you doing?
We're doing great over here, thanks, Maggie. Yes,
I think the time is almost up. Select your alien and bring it on down.
Yeah, let's go for this one. There we go. Thank you very much.
Madhu, how's your section doing?
Lots of choices here.
Lots of choices. I know. It is very hard. My apologies.
Very, very, very creative. Yeah, that one. Yeah.
OK, yeah, pass it along, please. Thank you. So, guys, thank you so much for participating in Draw That Alien. OK, let's look at the results.
Okay.
So, Tim, I think we'll start with you.
Right, we ready?
Show me the alien on your planet.
TRAPPIST 1E. Here we go. There we are. We've got an alien that clearly has to protect itself from radiation.
Yes.
So it's already developed this complex life form that has shelter. There.
Okay, yes, built-in umbrella.
Has the ability to walk on the rocky planet, obviously, and support its own body weight on that planet as well. So
fantastic.
there we have.
So there we have
TRAPPIST 1E.
it. Yes, that is the alien. And Madhu, what do you have?
So we have a simple tardigrade-like planet. You want to go simple on this planet. We didn't want to make too many guesses.
Okay.
Too much complexity. So,
Okay,
so I'm happy
lovely.
with that.
So you've got here, so you have tardigrade.
Simple life form
Yes,
on an ice-covered planet.
Okay, perfect. And water. And we've heard that tardigrades can survive sort of very extreme
Harsh
environments.
conditions, yes.
Okay, and this is what I got from my group. Let's get it the right way. So very good, I think, artistics here. And I'm going to put that in. And what do we have here? So we have a sort of a bulbous alien with a number of tentacles. I love the eyes, and the eyes are quite spread out. And so it gives it a sort of a good viewpoint. So I think those are wonderful examples of sort of alien life on other planets. So I think a round of applause for everybody who drew an alien. But first of all, I want to say that now each of you is an astrobiologist, because astrobiology is a sort of the science of trying to work out what kind of alien life you'd find on these exoplanets. So pat yourselves on the back, you're astrobiologists now. But now this is the bit I've been waiting for most, because I think Tim, you and you, Madhu, have drawn your own alien, and I must admit I've drawn mine too. So Tim,
Okay.
let's put these down, and could you get out the alien you drew? So this is an alien living on your planet.
Yes, yeah. So this was my alien on TRAPPIST 1E that I drew earlier.
Fantastic. Madhu, what have you got? So this was actually drawn by you, wasn't it?
We tried. So,
So you put it in the sand?
yeah, with all the courage I can muster.
Actually, this was your worst nightmare, wasn't it?
It
Happy
was
as
indeed.
scientists.
It was indeed. Science is the easy part. So,
Maggie, did you draw one?
Oh, me? Well, actually, I didn't have much time.
Right.
So I just threw something together, but I've
Okay.
just got it here. And, yeah, so it's a bit rough. So, yeah, apologies.
Oh.
But, yeah.
right.
Oh, right.
Yeah.
Right.
But
This is just something I threw together.
No,
There's not
Maggie-
much time. Let's
yeah,
just put that there.
yeah,
okay.
yeah,
So,
yeah.
I mean, if we were going to vote, I wonder whose would be best. I mean,
did you really?
Did
you draw
I,
that?
I think that's enough of
very
that.
convincing.
Yeah, thank you so much for participating. I think that's enough of Draw That Alien! Thank you. I better not be a game show host anymore. So thank you both, guys.
Thank you very
And I
much.
think I'll be
Thank
seeing
you.
you again later.
Thanks,
Thank
yeah.
you. So, we've been talking about the search for alien life out there, looking at what compounds might be found in an atmosphere of an exoplanet far, far away. But what if we wanted to actually go out and find these aliens? Now, our nearest exoplanet is Proxima b, and it's actually a rocky world, and it's about sort of 4.2 light years away from Earth. Now, that sounds like it's worth a visit, but just how far away is that? So a light year is actually the distance that light will travel in 1 year. And that turns out to be 9.5 trillion kilometres. So that's 9.5 with 11 zeros after it. So there it is. So the distance to our next door neighbour star is 40 trillion kilometres. So what if we wanted to travel there? Until recently, the fastest we could travel in space was about 1,600 metres per second. It's nowhere near the speed of light, but it's still pretty quick. Now, if we could travel at that speed and travel out towards Proxima Centauri, that journey would actually take 76,000 years. And that's just going from our star to the next door neighbour star. So what we need is a faster way to travel. Now, there's actually a project going on right at the moment, and it's called Breakthrough Starshot. Now, instead of carrying heavy fuel on board the spacecraft, what they need to do is make it light and agile, but what we do is we use a massive solar sail. Now, I've got a little demonstration to show you how this works. Fantastic. Ha, I have the water. Fantastic, thank you. So what I'm going to do is going to pour some water in here without making a mess. Whee. And then what we're going to do is add our boat. There's the water, and there's our boat. OK. Now, we've actually used this technology, and in the past, we've used light from the sun to accelerate things through space. But what we want to do now is we don't want to just use light. We want to generate our own light. We want to use lasers. What we do is we're distributing balls throughout this section. Now, each one of these balls represents a photon of light. So this is laser light. So what we need is a sail. And so what we're going to do is get a solar sail. Bring on the solar sail! And here it is. So this is our solar sail. And what you'll see is it's made out of very, very light plastic. So now what we have here is our solar sail. Now remember, what we have here in the audience is each one of these balls represents a photon of light. And now I want you to throw them towards the solar sail. So let's go. I'm sorry. First of all, I'm getting out of the way. Okay. And so what I want to do is I want to count 3, 2, 1 and throw them at the solar sail. So are you ready? 3, 2, 1. Throw your photons. Okay. Okay. So your photons hit the solar sail. Okay. Okay. We've still got incoming photons. I thought this would be a problem. But yeah, no, apart from getting bogged down, look, our solar sail has made its way all the way across, out beyond our solar system to the other end of the trough. And so this is the plan for Breakthrough Starshot. Up here, I've got a picture of a real solar sail. So this is what we're designing. This is the solar sail, and you can see it is very much like this sheet of metallized plastic, but it sits in space, and it is absolutely ginormous. Now, as I said, in the past, we've used light from the sun to accelerate them, but what we need to do now is use these photons of light, this laser, so we will send a pulse of laser light into space. Now, you only need a pulse of laser light because once you accelerate the solar sail, because we're in the vacuum of space, there's nothing to slow it down. So you accelerate the solar sail, and we have very tight pointing accuracy, and we point it towards Proxima b. Now, we can actually set this up and we can point it towards Proxima b, but we have no means of slowing it down. So as it approaches Proxima b, it will fly past, but what we want it to do is take photographs. So as it flies past Proxima b, it will take photographs of that exoplanet, and it will bring those photographs back to Earth at the speed of light. So even then, it will take 4.24 years to get those images back. But if we do this, we might be able to get closer to the answer of, are we alone in the universe? But there's a few things to say. If we can get this technology to work, then we can actually accelerate this solar sail to about 1/5 of the speed of light. Now, I'm a Trekkie, so that's warp factor 1/4, but the probe we can send can weigh no more than 1 gram. Because if it's any heavier, it has inertia, and so then we'll need more energy to accelerate it. If we actually get up to 1/5 of the speed of light, that journey of 40 trillion kilometres, it won't take 76,000 years. We'll be able to do it in just 20 years. Thank you very much, and a round of applause for our volunteers. With a solar sail, we can get something very small and lightweight out to an exoplanet and take photographs and bring them back to Earth. But my dream has always been literally to travel to the stars. So what if we wanted to get something a bit more massive, something like me, out to the stars? Well, there is also a new way of thinking about it. We're talking about the Alcubierre drive, and this is a theoretical way of travelling into space, and it's been developed by Miguel Alcubierre, a Mexican physicist. And what he's suggesting is that we actually, we manipulate space and time itself to travel out into space. So now for this, I'm going to need another volunteer. I always hate doing this. OK, actually, would you like to come up? A round of applause for our volunteer. Thank you for joining me. Now, first of all, what's your name?
Fakaya.
Fakaya.
Yeah.
Very nice to meet you. Now, what we've got here is my Alcubierre drive. Now, if you can put your feet just on the edge there, this is planet Earth. And at the other end of the carpet is Proxima b. Now, this carpet represents space and time. And that's something that Einstein came up with, the idea that we can take three-dimensional space and time and smush them together. So this is the space-time carpet. And out there, yes, that is Proxima b, and we want you to travel there. Now, first of all, what I want you to do is just take one step and get to Proxima b. So give it a go. Yeah, that's, woo. That's big, but not big enough. OK, so if you want to come back here, thank you very much. I'm just going to sort of straighten up, space and time. Just even that out. OK, so now travelling conventionally, it will take a sort of quite a while, as we've worked out, to get to Proxima b. But what if we can actually manipulate space and time. So what we're going to do is we're going to scrunch up space and time in front of you. So this is the principle behind the Alcubierre drive. Rather than trying to take that big leap, what we do is we concertina up or scrunch up space and time. So now when you take your step, it's quite easy. So because we've manipulated space and time, scrunched it all up, we have effectively brought Proxima B towards you. But that's not all we do, because we've scrunched space and time up in front of you, but what we need to do now is elongate it behind you. So now this is it. With the Alcubierre drive, we scrunch it up before you, and we elongate it out behind you. So there we have it. You have travelled from Earth to Proxima B in just one leap. So a round of applause for our volunteer, please. Thank you. So this is something that's been worked out mathematically. Mathematically, the Alcubierre drive seems to be a feasible way to travel in the future, but there are a few caveats. One of the things is, for actually to scrunch up space and time like that and elongate it behind you, you need huge amounts of energy. And that's energy we just don't have access to at the moment. But maybe in the future, we'll find ways of making that energy and we'll be able to travel these vast distances in space. Let's assume that we've made it to another planet and there is some kind of life out there. But what are the chances of finding civilized life, intelligent life? What is the probability of just finding bacterial slime or something a little more sophisticated? Well, to make this discussion, I'm going to call back Professor Chris Linton. Now, back in 1961, Frank Drake came up with an equation, and it was trying to work out the probability of finding, I'll say, civilized life, and we'll define that in a minute, within our galaxy. Now, for this, we've got 7 volunteers, but I think we've already been pre-selected. And so would our 7 volunteers please stand up? And will you all get out your whiteboards, please, and your pens? Now, so each of the volunteers here in this line represents a parameter from the Drake equation. So this is the Drake equation here.
Yeah, so this is how you calculate. We're not going to think about probabilities. We're going to try and calculate the number of alien civilizations in the Milky Way galaxy that are there right now for us to talk to.
Okay.
So when we're looking for alien life in the galaxy, this is what we need to know. Are we going to stumble across aliens wherever we look?
Yes.
Or is it going to be really rare and difficult? So that's what this equation calculates for us.
Okay, Drake developed this equation back in sort of 1961, and then some of the parameters weren't known. But what we're going to do is actually go through each parameter and write down what you think. Now, Chris, I hate to say this, but you know, you're a bit of a Grinch, aren't you?
I am at this, yeah. I think I'm going to be a pessimist today, I think. So but let's see what the odds are, even if we think we might be a little lonely in the galaxy.
Okay,
but we know the first few terms, though. So we can start with the number of stars in the Milky Way. We know that from Gaia.
Actually, we spoke about that earlier. So we think there are 100 billion stars in our galaxy. So please, for the first term, so you are N star, and could you write down 100 billion? So that's 100 with 9 zeros behind.
That's right.
Okay.
Yep. And we know that pretty accurately, at least for astronomers. There might be a factor of 2 in there or something.
Yes, but we know that. Ballpark.
Yeah,
ballpark,
exactly.
Yes. And that's what this is about. Okay. So let's go on to the next. So what's the next term?
So the next one is how many of those stars have planets. And when I was growing up watching the Christmas lectures, we didn't know that at all. But we now do. We know that the Milky Way likes making planets. So we can more or less assume that every star has a system of planets going around it.
So this is function FP.
Yeah, so it's the fraction of stars that have planets. We're going to say 1.
Okay.
All of them do, more or less.
So yes. And so some might have more, some might have less. So could you put 1 on your scoreboard? Thank you very much. Thank you. Okay, so what's the next parameter? We've got NE.
Yeah, so this is the number of those planets that are capable of supporting life.
Okay.
So we could argue about what you need to support life, but maybe we think our kind of life. So you need water, maybe a rocky planet. Well, these are quite common, we found out recently. So we know Earth-like planets are common. So we might as well put 1 here as well. So I reckon every star that has planets, on average, will have 1 planet capable of supporting life. So that's a 1 as well.
Okay, but now we're going into what we don't know.
Yeah, we're going from the modern science to future science. So the next thing we need to know is this FL. So if we've got a planet that can support life, does it? What fraction of planets have life? And here, this is where my pessimism, my Grinch-like tendency comes in. So I think we haven't found life anywhere but Earth yet, and we've been looking. So I reckon life must be pretty rare. So, you know, this is a guess. Let's say 1 in 1,000 of those planets. 1 in 1,000. Yeah. So can you write that on your screen? 1 divided by 1,000. And then the next term
is an FI.
Yeah, so that's the fraction of those planets that have life where you get intelligence.
Yes, okay, so intelligent life.
Yeah. Now,
Okay.
again, there's just us. If
But are we intelligent?
Well,
Okay.
we're as good as it gets, Maggie, as far as we know. You and I and this wonderful audience. And I think you have to think it's taken 5 billion years of the Earth to get to here.
Yes.
And we've only just made it. So I reckon intelligence must be rare as well.
Ooh, okay.
So I'm going to say 1 in 1,000. 1 divided by 1,000 for this as well.
Okay, can we put that on the screen? So, yeah, so,
On the case already. This
yes,
is good. Yeah.
lovely. And can you hold it up when you've written it out? Thank you. Okay, so now what's the next thing?
Well,
We've
this
got
is FC. So this is the fraction of planets that have intelligent life.
Okay.
That are capable of and willing to talk to us.
Oh, okay.
So
Yes.
one way of thinking about this is maybe do they have radio? Have they developed radio? So, for example, if you think about the Aztecs or the Romans,
Yes.
past civilizations, they were intelligent, but they wouldn't be in this category.
Yes, and so it's the technological capability
Exactly.
to actually communicate.
So I'm going to use my recent argument again. We've only just in the last maybe 100 years started to do this. I reckon it's going to be rare. Let's say 1 in 1,000 again.
Okay, 1 in 1,000. Thank you. Let's get that
I
on
want
the
to point out,
scoreboard.
I could be more grumpy about all of these as well. 1 in
Actually-
1,000, I think, is quite generous. So hopefully we'll get some aliens at the end.
Okay, so that's 1 over 1,000 again. Okay, and then we're coming to the last term.
Yep.
FL.
Yeah, this is the most unknown term. So this is how long you last
yes,
as a civilization.
Yes.
So, well, we've got at least 100 years because we've been transmitting radio waves for about 100 years. So maybe I'll be generous. Let's say we'll last at least twice as long.
Okay.
So 200 years for the lifetime of our civilization. But the Earth will exist for about 10 billion years in total.
Okay, because we're about halfway through the life.
So
okay.
that's 200 divided by 10 billion.
Oh, okay.
So that's a really small number.
Sorry.
So if you write 200 and then divide by 10 billion. So we get more ignorant as we go along.
Okay,
But
yes.
we can guess all these numbers and then we can put them together and calculate the number of civilizations there are for us to talk to.
So let's do just that.
Okay.
Can you send all your sheets to this
shall I
end?
go and get them?
Yeah,
Yeah,
and
all
Chris,
right,
if you
if you
can go
pass
get
me
them.
these.
So if you pass them up, what we're going to do is put them into the Drake equation calculator.
Oh,
the
is that what
mystery
that
box.
thing is?
Yeah.
Okay, good. Was it expensive, Maggie?
Incredibly.
Okay,
We blew
good.
our budget on this, but I think it's
Excellent.
worth it.
And we're not going to ask how this works. Oh.
I know. So, okay, I think we're ready. I'm going to press the red button and we'll get an answer.
I'm gonna stand back.
Okay, so
Yeah.
3, 2, 1. Let's see if we can get an answer. Whoa. Okay, that's not good.
Is it supposed to do that?
Yes.
Okay,
That's what I'm going to go with, yes.
Right. Oh, hang on.
Oh, it was doing its calculation. Ooh, okay. So we have a scroll, and let's
course we
see what's
do.
on here. Fantastic.
So this will
Ooh, more
be
smoke.
our calculation of the number of civilizations in the galaxy that we can talk to.
Okay, so let's get this the right way round. Okay, so Chris,
Okay.
if you hold the other end.
So the number is...
Okay, so it's less than 1. We've got 0.00002.
It's not very many.
It's not very many at all. Do you think you might have been a little over-pessimistic here?
Well, I think I was quite generous, actually, all those 1,000s. But this is the point. So in this situation, if we're right about those numbers, we're it. We're
I know.
almost certainly the only civilization in the galaxy. You could multiply this by 1 million and there'd still only be 2
Yes,
civilizations.
and so yes, so if we took every star in our galaxy and multiplied it by 1,000,000 times, there'd only be 2 civilizations in our galaxy. So us and someone else to speak to, and of course they could be far, far away, so we can't actually communicate
So
with
if you
them.
believe the numbers that we put in, then you have a world, a galaxy in which civilizations appear and then disappear pretty quickly and they never talk to each other.
Yes.
It's very festive.
Well, actually, not very festive at all. I feel
No.
quite depressed. I think I'll be really. I don't want to be alone, and that makes me feel very, very lonely, Chris.
No, I should say, even if this is true, we should look anyway, because you never know, because
Yes.
there were things in there that we didn't understand. But of course, you can also change the numbers.
Yes.
And think
so-
differently about things.
Lovely. So, Chris, if you like to step over here, what I want to do is I want a slightly more optimistic approach. Now, when I think of an optimism, I think of someone who's travelled out there into space. Tim, would you mind coming down again? A round of applause
Maggie.
for Tim. Good to see you again, Tim. Now, that answer was a little depressing to me.
A little depressing. God, only 100 years left to go. Goodness me.
Yeah, wipe out. So, Tim, what I'd like you to do is offer some alternative numbers.
Right.
Okay. And first of all, so you've
Okay.
got 100 billion. Yes. and then it was one and one.
and one.
Okay, so if you put those on your boards and hold them up, so
that-
100 billion takes a little longer to write.
And that gets
Okay.
us to the fraction of planets that could support life.
Yes.
Okay,
So we
perfect.
agree on that.
We're on FL.
Yeah.
And I think the raw materials are abundant in the universe for life. Water and ice is everywhere, organic compounds. And on planet Earth, as soon as the conditions became favourable for life, life evolved. And so I'm going to go for one for FL.
Yeah, okay, so if life can exist on a planet, it will. That's what you're effectively saying. Okay,
Absolutely.
so perfect. Let's put a 1 there on the board and let's hold it up, please. Okay, so we got 1. Okay,
Right.
so go on to the next parameter.
Now, so FI, intelligent life, and I do understand Chris's point of view here,
Yes.
but given enough time, I think life finds a way. It's always going in one direction,
Yes,
and that's
evolving.
becoming more complex, evolving.
So what are we going to put on this?
I'm going 1. I'm all
Okay,
in.
1.
All
Okay,
in.
yeah, blah, blah. I
Absolutely.
love the optimism. Okay.
Right, FC.
FC, yes.
Will that intelligent life communicate? Again, I'm taking the positive view that intelligent life at some point will ask itself the question, am I alone in the universe? And I'm going to try and communicate with other intelligent species out there. So that for me is a definite 1.
Okay, perfect, lovely. So let's put 1 on the board
Suppose
and turn
we
it around.
exist and we've done it, so I guess there's a logic there. Yeah, fine.
And, we're not that intelligent, so yes. Okay, so then the last one.
FL. So I'm
Yes.
going to take Chris's rather depressing 100 years.
Oh, yes.
And say, actually, as a species and intelligence, it solves problems.
Yes.
And our technology is getting better and better. Our life expectancy is improving.
Yes.
We're able to overcome problems. Our
Yes.
medicine is getting better and better. There's every indication, every potential that if we collaborate and work together, we'll last as long as this planet can maintain us here.
Which is about 4.5 billion years into the future. I like this.
Absolutely.
Yes.
And so that will be half of the entire solar system's life.
Yes,
So we're going to
perfect.
have to put 0.5
Okay,
for our final
0.5.
one.
So what we need to do is gather these results up and put them in the Drake equation calculator.
Okay,
So,
I'll
thank
go
you.
grab
If you can bring these down.
All right, can I
Now,
have these
this
ones,
is looking
please?
a lot more
Thank
positive.
you very
Thank you.
much.
Yes.
I'm going to stand over
Thank
here.
you.
Okay.
I'm going to let you and the astronaut be next to that thing. So I do my science at a computer. I don't use those
Yeah,
things.
the snake was a bit worrying. That's all I can say.
It's
All right,
perfectly
Maggie.
safe.
Fantastic.
Here's
Here we
the
go.
more optimistic version.
Fantastic. Now let's put this in. Put them all together. Let's slot them in. Thank you. Okay. We are getting the calculation. So let's hit the red button. So let's count down. 3, 2, 1. What's the answer? Ooh, okay, we're getting the smoke again. We have a pope.
Okay. Yeah.
Ooh. So we're getting this. Oh, hey, what's this? Ooh, this is looking promising. I like the look of this. Okay, so let's take this. Okay, I've got the magic scroll. Okay, so let's put this down here.
Okay.
And let's check this out. Okay.
Let's see what we've got here.
So
Are
Tim,
we
if you
ready?
can wait the other. So,
And this is the number of civilizations in the Milky Way galaxy.
yeah, and this is just our galaxy, the Milky Way galaxy. So okay,
Ready.
we've got 5. Sort of. Okay, 50. Oh, okay, 50.
wow.
Wow.
1, 2, 3, 4, 5, 6. Okay, so that is 50 billion. Okay.
Got a galaxy full of life.
That's a bit more optimistic.
No, that is very, very much more optimistic. Well, first of all, a round of applause for our volunteers. Please take a seat, and thank you very much. And thank you, a round of applause for our wonderful contributors to the Drake equation. Thank you, guys. Thank you. And so we came up with some interesting answers there. It was never actually going to give us a definitive answer because we don't know, we don't have the right information accessible yet. We think that there must be life out there, but the problem is it might be far, far away. So if we could find the aliens, the question is, what sort of thing would we like to say to them? Now, we've been polling people who've come into the studio, and this is the result of what they want to ask aliens.
Do you like to sing? Do you like to dance? Because if you like to dance, you could have a competition. And yeah.
If you're thinking of coming on holiday to planet Earth, I don't know if it seems big or small to you, but there is huge variety, so you're going to need to take a while.
What do you look like? And is there other planets out in the universe that human beings do not know?
Do you have any hobbies that we don't know about here? Is there any materials that are undiscovered to Earth?
Where do you live and what's it like? And are you carbon-based? Do they get hungry? Do they ever eat for pleasure?
Is water really necessary for life? I think that's one of the big questions that we're grappling with here on Earth.
Hi, what's your planet like and what's your favourite things on your planet?
What sort of wildlife do you have? And do you speak English, or do you speak Spanish, or do you speak any other language?
And I want to know what the plants are and if you can breathe.
We are a beautiful planet, it's diverse, it's humans and animals and plants, and that's great, but so much has changed. And I think actually we would learn so much from meeting another off-world civilization.
Do you guys have a fascination for outer space as much as we do?
Aliens, please come to my home.
So yes, these are the messages we'd like to get out to aliens. Now, this has actually been done before because there were 2 spacecraft called Voyagers, and they travelled through our solar system and went out beyond. And this is the golden disc that were actually put on board the Voyager spacecraft. So Voyagers were launched in 1977, and they have travelled through space for over 50 years now, and they've gone out into interstellar space. And yet on board, they had these records. And these records, they are actually, so they were very much of their time. This is 1970s. So these are records, and we sent them out into space, but we also included instructions of how to play the records. And on this, they included all sorts of things. Like they included a map of where we sit in our solar system. They included sort of the laughter of children, sort of children of the Earth saying hello, and sort of the music of Beethoven, and many other things. Now, because this is the 200th Christmas lecture, I thought it would be wonderful to do the same thing. So what we've done is collected all those messages and put them on this disc. And now, I haven't got the capability and we haven't got the budget to send this into space. So what I'd like to do is please welcome the Director of the Royal Institution, Catherine Matheson. Now, Catherine, what I'd like to do is give you this disc that we've created, so our own golden disc, and hopefully it can join the archive here at the Royal Institution. So thank you very much.
Thank you so much, Maggie, and thank you to everyone who has contributed to this amazing record. It's a real privilege to have it here at the Royal Institution. It's a really special year. As you know, it's 200 years since the Christmas lectures were started by Michael Faraday to share the joy and wonder of science with young people. And that goal feels just as relevant and important then in 1825 as it does now. So thank you very much to all of you, and especially for being our 200th Christmas lecturer. Thank you, Maggie.
Thank you very much, and a round of applause for Catherine, please. So that brings us to the end of this lecture, and I must admit I'm tearing up a bit because, as I said, I used to sort of always want to come and see the Christmas lectures. I never got the opportunity, but I feel so honoured to be here with you tonight. Now, as a child, I was at the back of the class. I wasn't considered very bright. I went to 13 schools, and I have dyslexia and ADHD, so I never thought I'd be standing here in front of you. But I think this is the key: have a big, powerful dream and see where it takes you. All my life, I have been reaching for the stars, literally. I have wanted to get out there. And in this lecture, we have done just that. We have gone to the very edge of the solar system. What I hope for in the future, and especially for you young people, is that as we make that journey, we do it in the right way. We do it for the benefit of all humanity, and we learn from our past mistakes and make sure we actually go out into space in an essence of unity. So thank you very much for having me here, and thank you also very much for support from CGI. And for that, that's it from me. Wishing you all a very, very merry 2026. Thank you very much. And good luck. Think you've got what it takes to run a space mission? Step into command with the Open University's interactive experience and meet the experts that make it happen. Scan the QR code on the screen or visit connect.open.ac.uk/RI2025.